Intersection and union. First, the intersection of two sets is the set of elements common to both sets. In this example, the number 1 is in both sets, and therefore 1 is also in the intersection. 2 we can see is in the first set but not the second. 3 is the next number that's in both sets, so 3 is also in the intersection. And 4 is in the first set but not the second. 5 then is the last number that we see in both sets. Going on to union, where intersection is generally a set that is smaller than the two sets that went into it, union is just the opposite. You take the union of two sets, you generally end up with something bigger. It's going to be the set of elements that belong to either set. So that means we can start by entering every number from the first set, 1, 2, 3, 4, and 5. And then we can add to this all numbers that are in the second set that we haven't already listed. We already have 1, 3, and 5. We still need to add 7 and 9 to our list. So when we're taking an intersection or a union of discrete sets, it's simply a matter of listing the elements in this way. The definition is the same for continuous sets, but the way we find them will feel rather different. Here we have two continuous sets, and by that I mean these are infinite sets, the set of all x such that x is less than -5, for instance. This is an infinite set of values. If I graph both of these on a number line, I have -5 and I have +2. Let's graph the set A using blue. So less than -5, that means from -5 to the left. And then we'll graph the set B using green. Greater than or equal to 2 means from 2 to the right. And I used a square bracket for B because of the greater than or equal to. I used a round parenthesis for A because of the strict inequality. So first of all, let's find A union B. The union is all elements of either set. So that really means, so if we graph the union up here in pink, it means everything that's on one graph or the other. So everything that's on this graph and everything that's on this other graph. The only way we can write this, because these two intervals don't overlap at all, this is what we call a disjoint union. The only way we can write this is as a disjoint union of two intervals. So the first one is from -infinity up to -5. We put a union symbol, and the second one is from 2 to infinity. The intersection of these two is the overlap, because it's the elements that are common to both sets. So that's where the two graphs overlap. And since we can see that these two sets don't overlap at all, they're completely disjoint, the intersection is the empty set. Going on to our next example, we're going to do this the same way by graphing the two sets. So here's our number line, and I will again graph A in blue. We've got x such that x is less than or equal to -1. So let's plot our two numbers first. We've got -8 and -1. So here's our -1. Here's our -8. Very important to get them in order. Scale is not so important here. We're just looking for the idea. So less than or equal to -1, that's going to be my set A. And then B, we will graph in green here. B is greater than or equal to -8. So this time we can see that the two sets do overlap. But this time finding the union, let's do that in magenta again. The union is the set of all values that are on either graph. And in this case, when we put the two graphs together, we can see that they make up the entire number line. There's not a single value that isn't on one graph or the other. So A union B would be the entire real number line, or the interval from negative infinity to infinity. Whereas the intersection, as we already mentioned, is the overlap. And therefore the intersection, we can fill in here the region where these overlap. And this would have square brackets. And therefore the intersection is the interval from -8 to -1. Generally what happens is that given two continuous sets, often the intersection will be sort of a normal case and the union will be a strange case. By strange, I mean the whole real number line. Or the union will be sort of the normal case, as we saw in the first example, and the intersection will be a kind of strange case, in this case the empty set. By strange, I mean just doesn't really relate to the particular values we were given. Going on to our next example, let's start by graphing both of these. Note that it is really necessary to graph or at least visualize the two sets before finding that union or that intersection. I would say the most common mistakes on these problems are when people just assume that all of them follow the same pattern, and they tend to just go straight to the answer without stopping to think about it. So let's do again the set A in blue. That's going to be greater than -2, which looks like this. And we'll do the set B in green. That's going to be greater than or equal to 4. We can see that what's unusual about this case is that both of these graphs go in the same direction. We're still just going to think about our union and our intersection based on the definition, right? The union is all values that are on either graph, one graph or the other. So it looks like -2, and we're going to keep going in this direction. We're never going to find any values in this direction that are not on one graph or the other. Whereas our intersection, this starts where the overlap is, which is up here at 4, right? So my intersection starts at 4 with a square bracket and goes to the right. So it looks like both my union and my intersection are semi-infinite intervals, meaning that they go off to infinity in one direction. My intersection goes from 4 with a square bracket, and my union goes from -2 with the round parenthesis. So what happened here is that one of these sets is a subset of the other. In fact, B is a subset of A. When you're in this situation, the intersection is going to be the subset and the union is going to be the superset. But rather than trying to memorize that as a general rule, we just want to kind of observe why it's true and be able to figure it all out, again, from first principles whenever we have to.